Okay, on to questions 4 and 5. So question 4, the C code below should wait for a button connected to PA15 to be pressed. The button is active low when pressed. Describe two problems with the code. So we're looking for, a change from high to low. So that's, 1 to 0 there on the button. That's what we're trying to find. And it's asking us to look for two problems with the code. So let's look and see what's going on here. We've got an unsigned int star GPIO IDR equals unsigned int star, and then an address. So let's actually pull up the manual here and go ahead and look at this. I got to change my configuration a little bit. And let's find the GPIO registers here. And let's look at what these values are. We know that GPIO-A does start at 480000, but I think we're looking at a wrong offset here, and let's just verify that IDR is at offset 0x10, and so that is one of the problems there. That should be 10 for the offset for IDR, if that's what we're looking for, and that's what we should be looking at if we're trying to figure out if a button is pressed, because that would let us see if a value is changing for something connected to the board. We're looking at PA15, so this something shifted by 15 looks probably like it's right. But we're doing a while the pin, and actually this is a mistake here. This should be GPIOA IDR. That's a mistake in the edits here. GPIOA IDR ended with 0 shifted by 15. So 0 shifted by 15 is still 0, right? If we shift a 0 by any amount, we're shifting in zeros from the right side of the number, and we're going to end up with a bunch of zeros again. And then we AND it, and that's going to be 0, which is going to evaluate as false. So this will happen one time, and then it's going to fail. So this 0 here should be a 1, because what we really want to do is look at that single bit of GPIO-A IDR. We want to see if bit 15, which corresponds to PA15, is a 1 or not. And so that's what we should be looking at, is a 1 shifted there. The other issue that's in this code is that this should probably be a volatile, because we're reading something from memory that the compiler doesn't know if this value is changing or not. So it's important to tell it, hey, this value is going to change. You're not going to be aware of it, so don't optimize away my code. So that's it for that one. Really, we're looking for this error here, the volatile error here, and then the 1 shifted by 15 instead in the check to see if it has changed. Moving on to question number 5. On pulse width modulation, it does say see page 1016 in the manual. I'm going to go ahead and pull that up here. So we can look at that, and it's the functional description of the time-based unit, and the important part here is the part where it says the counter clock can be divided by a prescaler. The auto load reload register, the prescaler register can be written to, etc. And really what this description tells you is that prescaler is there to subdivide the clock. And the way that it works is when we're counting up to our value in ARR, or counting up to our value in CCR1, instead of counting every cycle, we count every PSC plus 1 cycles. And so that prescaler effectively makes us count a little slower, and therefore take a longer time. We haven't been using that this much because the timers are already pretty big and the clock's already pretty slow. So we can get pretty long timers just natively in the 32 bits that we have for the general purpose timers. But this allows us to get a longer timer for, say, timer 4 and 5, the ones that are timer 3 and 4, which are the ones that are 16 bits in the general purpose timers here. So let's go ahead and do our calculation. ARR equals 1,000,000, CCR1 equals 200,000, PSC equals 3, and the clock is 50 megahertz. So we want to know the duty cycle and the period time. So let's find the period time, and that P time is going to be related to our ARR value, clocked at this many cycles, multiplied by our prescaler. So our P time is going to be ARR times PSC plus 1 over FCLK, our frequency of the clock. And this is just taking this from the notes on chapter 14. I'm pretty sure that equation is verbatim in the notes there. So to do this calculation, we're going to just plug and chug. So 1,000,000 times PSC is 3, so 4. So 4 million over 4 sorry, we are using a different clock here, so 50 mega, 50 million, and that should get us a period of time of 0.08 seconds equals 80 milliseconds. So our period time is 80 milliseconds. The duty cycle, we can either give that, it says give both answers in milliseconds, so we're not looking for the percentage. We can find the duty cycle in two ways. So we could plug and chug this same equation, but replace ARR with CCR1, and that'll give us the number of cycles or the time that it'll take to do that at this PSC and clock rate. The other thing we can do is just figure out what the duty cycle percent is. So if we do 200,000 divided by 1 million, that gives us our duty cycle percent. And that'll be how much percent of that 80 milliseconds is devoted to the duty cycle. So this gives us 20% here, and that means 20% of 80 is going to be our duty cycle, which is 16 milliseconds. Moving on to part B, we're going to do the same thing, so plug and chug into P time, and that's going to be 500,000 times PSC plus 1, so times 8 over 50 million hertz, and we're going to get again 80 milliseconds out of that. And let's go ahead and do P or not P time, but in this case let's do D time for the duty cycle time. So if we plug in 100,000 times 7 plus 1 is 8 over 50,000, or 50 million, excuse me, that'll give us again 16 milliseconds. And so that's our duty time is 80 milliseconds, and our period time is 80 milliseconds. Our duty time is 16 milliseconds. And we could have found the same thing by doing 100,000 divided by 500,000. That would give us 20% again, and so we'd know it's 20% of 80 milliseconds. This problem is mainly to show you that we can have different values for ARR and CCR1 and get the same duty time if we have a different prescaler. So we've got double the prescaler value, right, 4 to 8. We halved our ARR and CCR1. We're at the same clock rate, so that gives us the same timing. So that allows us, that prescaler sort of allows us to adjust how fast we're counting, and therefore get maybe longer timers with a smaller AAR or CCR1 value if we're going to exceed that 16 bits on timers 3 or 4, or the 32 bits on timers 2 and 5. That's it for those two problems.